Hi everyone, let's begin in like 5 more minutes. Sorry for the delay. I'll be here in 5 minutes. Hi everyone. I think I failed to unmute my mic. Yeah, so let's just dive into this week's questions directly because I am assuming that most of you would have seen the videos and so we'll solve some questions today. So before that, I believe just to give you a small short context, in the last class we were talking about the internet and routers, the role of routers, right? So essentially we have the internet is made up of routers like this, and then we have packets that come and hit the router and packets that leave the output interface. Is the input interface, the ingress, and then egress. Right? So what happens once a packet enters the router? So how is the router hardware designed? Correct? How is the router hardware designed? And what algorithms are used for comparison? Because as we are talking in the last class as well, what is the whole process of routing based on? It's based on something called IP addresses. Correct? So what is an IP address? It basically it's a 32-bit number which is divided as 8 bits dot 8 bits dot 8 bits dot 8 bits. Right? So every packet that comes to the ingress interface will have an IP address. So every packet, let's say a packet looks like this. Now this will have an IP address, a source IP and a destination IP. Now this is added on to the network layer, right? And if any of these concepts are still not clear, you can always ask me, right? So I think I should do this. Right. So every packet has a network layer which has the source IP address and the destination IP address. So whenever a packet comes into the router, right? This is the router. So a packet is coming inside the router. So it has to make some decisions and put the packet onto, let's say there are multiple outputs here. Okay, this is route 1, route 2, route 3. So it has to take this packet. So first, take the packet in, analyze the packet, correct? But analyze the packet, what does it see? It sees the IP address, correct? And then it compares the IP address with its routing table, and whatever based on whatever is there in the routing table, it puts it onto the particular route, route 1 or route 2 or route 3. Okay? Then find the appropriate hop. These are also called hops. Let's say hop 1, hop 2, hop 3. So essentially, this is what happens. So this week, what was spoken about was all of those specialized algorithms which are used to store the lookup table, or rather, um, how is this routing table or the lookup table stored? How is this stored inside the router? And what is the algorithm that is used to compare the IP address that we see on the packet with what is there in the table? Right. So, I mean, this must be a very trivial question to you. What is the big deal here? Like, oh, it's. I mean, why do people worry so much about it? Right. Like, uh, you can just compare it, right? I mean, it's like if in your C program you write, if this equal to this, then do something. Right. That's pretty much what some of you might have in your head. So, why is this important? Is because in this router it handles huge packets, huge number of packets. So it is at the TBPS scale. That's a huge scale. That's a lot of packets, right? So anything that you do for one packet gets magnified by the number of packets that you expect per second there. So here you expect millions of packets per second. So your computations have to be very, very clear and very, very concise. If it is not, then your computation complexity will explode. So which is why these algorithms came up, and these algorithms are described in a book called Network Algorithmics. Algorithmics by George Verghese. Okay, I mean this is the OG book, the original book that has these algorithms in it. So more importantly, today we'll be looking at mostly these two because most of the questions are based on these two uh, algorithms only: a single bit try and then path compressed try. Right. So we'll just like that, we'll draw some of these tries and then get you ready to answer these questions. Okay. So let's just dive into one. Question number one is, if you know the answer, you can always put it on the chat, right? So which among the following is true when a trie constructed with a set of prefixes resulted into a full binary tree? Right. So what is a full binary tree? It is basically something like this. Right, which means all the nodes are available. So what is an incomplete binary tree? So this is a full binary tree. So what is an incomplete binary tree? It will look something like this, let's say. So this is incomplete because for the number of the height, which the number of levels are 2, the height is 2. So it needs to have the number of nodes that fill it up, right? So which means in what case will a try bit level single bit try uh, result into a full binary tree? So is it right? Okay, so now only binary try has the best lookup and update complexity. Is it A, or is it B, where only path compressed try has the best lookup and update complexity? Okay, let's keep it aside. And then C is both binary and path compressed tries have the same lookup and update complexity, or is it D? um, binary trie and path compressed tries have the same lookup complexity but different update complexity, right? So the only time when the trie constructed with a set of prefixes which will result into a full binary tree, this will also translate to the fact that a path compressed tree will also have similar characteristics. So when the trie is constructed with a set of prefixes, so which results in a full binary tree, there are no nodes with a single child to compress. So that means the path compressed trie, right? The path compressed trie will resemble a regular binary tree with a height of log n base 2, thus, where n is the number of keys. So in a full binary tree, since each level of the tree has the maximum number of nodes possible, both binary and path compressed trie with full binary tree shape will have the same lookup and update complexity. So this is the correct answer for this, right? Just think about it from a perspective of, okay, when will both of these cases be true, right? Uh, so if it is a full binary tree, then that means both path compressed and binary are the same tree. There is no difference. So binary and path compressed will they look similar. You can't compress anything there. That's what it means. That's a tricky question, but yeah. So that's the answer to that. So given a routing table having 5 prefixes with prefix length of 0, 2, 4, 6, 8, right? How many pointer references are required in the worst case for the binary trie? Okay, I'll give you a moment to start this. See, when they say given a routing table of having 5 prefixes, correct? So I hope you've all seen the video. So this is prefix 1, then the second prefix is, let's say, 0, 0 star, and then third prefix is, say, 0, 0, 1, 1 star, and then the fourth is 0, 0, 1, 1, 0, 0 star, 7, 2, 3, 4, 3, 4, and then 0, 0, 1, 1, 0, 0, 1, 1 star. So let's say this is P1, P2, P3, P4, P5. So it's something like this. Right? Imagine if this is the case. I mean, it is not exactly the case. Correct? What is a pointer reference? Now, if you construct a trie, you will have a tree something like this. Let's say 2, 3, something similar to that. Let's not construct it right now. It's just an example that I've taken. So the number of pointer references is number of times you have to compare the bits. So in order to reach P4, you have to compare 1, 2, 3, 4, 5, 6, 7, 8 bits. Right? So now they're saying this table has 5 prefixes, out of which the length are such and such. Correct? The length of P5 is 8 and such and such. So in the worst case, how many pointer references are required? The worst case, how many pointer references would be required? The worst case pointer reference is the highest one, right? Because if a packet comes and if it gets matched with P2, then it's well and good. If it does not get matched with P2, then it'll go and check P3, P4, and worst case, maybe it'll go to P5. So that is it. It's a very simple question. So the worst case itself is the answer is 8. So the answer is 8 here. Right. So is that clear? Right. So basically, again, just to paraphrase whatever I just said, in the worst case scenario, all the prefixes have different lengths, and the binary trie would have to store all 5 prefixes at different levels of the trie. The number of pointer references required in this case would be equal to the number of levels in the trie. So since the longest prefix length is 8, right? In this case, it's 8. The binary trie would have 9 levels, including the root. If you include this root, it'll have 9 levels. However, the first prefix with a length of 0 can be stored directly at the root. So it does not require a point reference, and therefore the number of point references required in the worst case for the binary trie would be 8. This is kind of self-explanatory. So I mean, if you can just yeah. Now, the third one I think is something that we just discussed. It's an extension of the first question actually. Right. In which case will a path compressed trie resemble a regular binary trie? Right. So in which case would it be? So as I was saying, the very first question, when the trie is full, right? When it's full in the sense, it's a complete binary tree. So the trie is full. Each node has the maximum number of children possible. So in this case, there are no nodes with a single child to compress. Right. And the path compressed trie will resemble a regular binary trie with a height of log n raised to, where n is the number of keys in the trie. Right. So this is an extension of the very first question that we discussed. So it's simple, right? Okay. Now let's go into the big ones. Okay. Let's try and construct a trie here. So consider the prefix database table shown below. What is the height of the trie constructed using a 1-bit binary trie? Right. So 1-bit binary trie. This is the very first data structure that was explained. I'm completely speaking with the assumption that you've all seen the videos. If you've not seen the videos, please feel free to like unmute and ask me questions, or just put it in the chat window. Right, okay. All right, so these are the prefixes, and let us construct a trie. It'll be like this. So now, as usual, you take P1 and then you just keep it there. This is the first state, which is star. So whenever there is a 0, you go left. Right? I mean, I'm just giving you these basic mechanical rules, that's all. And then you label it as 0. And then what is the level there? Which is P2. So this is done. This is done. And the next is P3. P3 says 1 star. So because we've already added 0, now there is 1. And then now we say P3. Okay? So what are done? First 3 are done. Correct. And then P4. P4 is what? 1, 0. So 1 is already here. Now I have to add, 1 is already here. Now I have to add a 0. So 1 and then 0, and this becomes P4. Right. The next is P5, which is 1110, which is 1, another 1, and another 1. This becomes P5. Correct? The next is P6. P6 is 1000. So 1. So 1, we can see 1 here, and then 0, and then we need to add 2 more zeros. This P6, right? P6 is done. Next is P7. P7 says 11001. So let's say this is 1 and then 1. So we already have 1 and a 1, and then we need to add 0, 0, 1. So this is 0, this is 0, and then a 1. And this is P7. Now P7 is done. So P8, 1 followed by 5 zeros. Correct? So for P7, it's 1 followed by 5 zeros. So this is 1, and then there is 1 0, 2 0, 3 0. Then you have to add 2 more zeros. That's all. 0, and then another 0, and then this becomes P8. Okay. So P8 is done. And then next is P9, which is 1 followed by 5 zeros and a 1. So this is 1 followed by 1, 2, 3, 4, 5 zeros, and then finally a 1, right? And this becomes P9. All right. So now what is the question? So we've built the binary trie right now. So what is the question? The question is, what is the height of the root node, which is P1, right? So I mean, what is the height? Sorry, what is the height of the tree? If you consider that the root node is at height 1, the height is 1, right? So height is basically nothing but the depth of the tree. So from here, if you calculate the number of hops, let's say this is 1, and this is 2, 3, 4, 5, 6, 7, and 8. Correct? This is the longest prefix here. So the answer is what? The answer is 8. That's it. And funnily enough, you do not even have to construct this trie. Because this is a single bit binary trie, you can just look at this and say, 1, 2, 3, 4, 5, 6, 7, right? If there is 7, add 1 to it, and then this is going to become 8, and that's your answer. And why are you adding 1 here? Because they are saying the root node is at 1. So this is a shortcut to answer such questions. You don't even have to construct this. But this only applies for single bit binary tree, 1 bit binary trie. Okay. Okay. Now consider the same table shown above, but You have to try drawing a path compressed trie for the same tree. Okay, so let's do this. We just drew this trie above, correct? It's the same. The question is the same. It's the same. The table is the same as above. So now, when it comes to a path compressed trie, we can optimize some aspects, like the number of times we'll have to encode the same prefix types. Like there are two zeros, you can compress this into a single node, right? So when you do that, what is the height of the tree is the question. Okay, so what are all the places where you can compress? Can you compress something here? No, you can't. Can you compress something here? Okay. Can you compress something here? No, you can't. But and can you compress something here? No, you can't. Can you compress something here? No, you can't. Can you compress something here? Yes. So this is a yes. So you can make a compression over here. Okay. And here, can you compress something? No, you can't. And here, can you compress? Yes, you can. And here, can you compress? Yes, you can. Because there are two zeros. Here there are two zeros. Here there are two zeros. And here, can you compress something? No, you can't. So we need to compress this, this, and this. So how do we do this? This is how we do it. We abstract this node into this. So basically, this node becomes P8, and this node becomes P6, and this node becomes P7, right? So these two nodes. And yeah, so I think yeah, so I made a mistake here. So basically, see, for this part, you can only compress on those areas where there is a particular prefix. So here, in this case, you can basically compress this part. So what will happen? P7. So this will be abstracted into P7 basically. So this is what the final trie would look like. So this is P1. So basically a star. This is P2. Goes there with a 0. And then this is P3. Right. And then now we go to a 0. And then we say P4. Right. So far, no compressions have happened. And then we are adding P5. Here also so far no compressions have happened. So far it's the same as the single bit try. And then now when we're adding P6, correct? So we are doing the first compression here. It goes like this, P6. But what are you giving here? You're saying the skip is equal to 1 and the segment is equal to 0. So this is P6. And next, P7. So P7 is 11001. So 110, and I said we can compress it. How? By saying the number of times I'm skipping here is 2. And what am I skipping? The segment that I'm skipping is 0 and 1. So there's already a 0 here, and then I'm skipping 0 and then 1. So this becomes P7. And then P8. P8, it's going to be, yeah, a 0 and then a P8. But the skip is what? Skip is equal to 1 and the segment is equal to 0. And then finally P9. Right, so I would like you to just take a look at this and see if you have any questions, because I'm assuming that you would have understood the basic formation of a trie. If you want me to explain from the scratch again, you can let me know. I can do that as well. Because the next questions will be very similar to this.
Sir, what is the current answer, sir?
Oh, okay, yeah, good question. Right. So again, the question was, what is the height of the trie here? So what is the height of the trie? We are keeping this as height as 1. So 2, 3, 4, 5, 6. So the height is, answer is A. Okay. Right. So let's move on. Oh, did I just do something stupid? Okay. So this question is talking about TCAM. So what is TCAM? TCAM is ternary content addressable memory. Right? This is called TCAM. So these are all, so TCAM is nothing but a very special type of memory which is there in routers. So this is high speed and it can do parallel lookups. So what does parallel lookup mean? So when you want to compare something with a table, what do? We go here first and then check, is it matching? And then we go here and then we go here and then we go here and we go here. This is what we do. But parallel lookup means at this one single clock cycle, it can compare that particular input with all of it and then find out which is going to be the correct uh, hop. This is the advantage of TCAM. It's high speed and parallel lookup, but it's got a lot of gates and a lot of physical mappings, which makes it very costly. The memory is very costly, right? So this is the prefix table that's shown. Okay. So the question is, which of the following prefixes should be merged to reduce the size of the table for storage in TCAM? Okay. So what do they mean by merging? So this table that you see here, it has some repetitions here. Okay. So what are the repetitions? So how do we figure it out? So if you look at P1 and P5, right? You can see that the next hop is the same. The next hop is 2 here. And the first 4 bits are the same, correct? So you can merge P1 and P2. You can merge P1 and P2. Give me a moment. Okay. So we can merge P1 and P2, sorry, P5, and we can say the entries are 1001, and then whatever I give after that, it should be fine because I don't care at this point, right? Similarly, where else can you find similarities? You see P2 and P4. For P2 and P4, it's 1111 and then start. I don't care what happens after that because the next hop is also 3. So both of these lead to hop number 2 and both of these lead to hop number 3. So the whole table now becomes this. So 5 entries have become 3 entries. So what are the answers? The answers are C and D. Right? Is there any other way you can match it? No, you can't. Okay. Okay, so they've given the table, the prefix table, and they're asking.
Sir, can you repeat the previous one, sir?
Oh yeah, sure. Okay. So okay, so basically this is the prefix table, right? And which of the following prefixes should be merged to reduce the size of the table for storage in TCAM? So there are 5 entries, and when they say merged, it means we have to reduce the number of entries. Right. Yeah. So step one, I'm giving you manual steps right now. Step one, forget about this. Now you only consider this one, and this one, right?
Yeah.
So when you consider these three, step two here is only look at entries with the same next hop, right? Why is that? Because how can you merge something when the next hop is not uh, the same? It has to be the same. So now, if you look at next hop of 2, what are all the entries that you have? P1, P3, and P5. Correct? And then if you look at a next hop of
Yeah.
3, we have
P3,
P2,
P4.
P2, and P4. So among these three, among these two, what all can you merge? Now the question becomes simpler. Now among P1, P3, and P5, correct? P1, P3, and P5, can you merge all the three? No. That's because you don't have commonality between all P1, P3, and P4. So the only common aspects here are the first 4 bits, and that's it. Now, because the first 4 bits are the same, you can say I'm merging P1 and P5. So among next hop of 2, P1 and P5 have been combined for the same next hop of 2 because it doesn't matter. It doesn't matter what is there after 1 and 1. I mean, you can always ask why am I not looking at these 2 bits? It doesn't matter whether there is 1 and 1 here or 0 and 0 or whatever is there after that. I'm anyway sending it to the next hop of 2 if the first 4 bits are 1001. So that's the logic behind merging here. You think about it from that perspective, right? I don't care what is that beyond it because the next hop is anyway going to be 2. Even if the prefix is going to be 1001, 1110, let's say, then also I don't care. If the moment I see 1001, I'm going to close my eyes and I'm going to send it to hop number 2. So because of that, we are merging P1 and P5 is merged. These two become one entry. P5. These two become one entry, entry number 1. And then P2 and P4. If you see P2 and P4, same case. So where is P2 and P4 coming? Now we have finished hop 1, hop 2, hop 2. Now hop 3, if you look at P2 and P4 are there. P2 and P4, do they have any common aspects? Yes, the first 4 bits. First 4 bits. Right? Do you understand this common part of it? Because right after this bit, it becomes 1 here and becomes 0 here. So now for P2 and P4, I'm seeing the first 4 bits and saying that after if I see 4 bits of 1 1 1 1, then I don't care what is beyond it. I'm just sending it to hop number 3. And so we are merging this and this and this and this. So it becomes from 5 entries. It becomes 3 entries. Right? Again, take a look at this. I mean, just see if you understood what I said. If not, I'll go through the same thing again. Yeah. If suppose if you have some questions, let's say, in why are we merging, or what is the logic behind merging it from left to right, or any such questions, it goes. So you can ask me any of this if it's clear or if it's not clear. So who asked the question? I could not see the name.
Actually,
Tirumala
sir.
asked the question.
Hello, sir. Excuse, sir.
Okay, Jay.
There is a common bit, common for P1 and P5, but there is no
Correct,
common
correct.
for P2 and P4, sir.
Are you sure there is no common?
The first 4 bits are for common for P1 and P1, P3, and P5. And at the
No.
same
Check
time,
again.
the second,
Check again. Check again.
the
You're
P1,
saying first 4 P1 first
first
4
4,
bits are what?
I think P1, P5,
P5.
P1 and
Okay,
both are common, sir.
correct.
And P3 also, one bit is differ. And compared to the P1 and P5 and compared with the P3.
So is it common for P3? So can you compare that? So see, for P3 it's 1101, right? It's 1001 1001. Correct.
At the same time, P4 and P2 and P4 are both are the first 4 bits are common.
Correct.
Extremely
Correct. Yes. Perfect.
most significant bits from there.
Correct. Most significant bits. Exactly.
Yeah, when but here we are going selecting P1 and P5 and P2 and P4. Both are two answers. The two answer will be correct.
Right. Exactly. Perfect. Correct.
But whereas in P1 and P2, P1 and P2 are different, P3, P1 and P1 and P3 also differ. One bit is different. But we are while merging, we are taking the just first 4 bits are consider best hops.
Okay. Okay. So I mean, I think your question is why are we taking 4 bits, or is it like you feel okay. Okay. So I couldn't understand your question. So if you can just paraphrase it again. So you're saying P1, P3. Okay. Okay. So just everything. I'll try to understand what you just said, and then we'll go from there. Okay. First, we are looking at P1, P3, and P5. Why? Because the next hop is 2, 2, 2. Correct? So far, so good. Sorry. So far, so good. This is clear. Next, among these 3 entries, we are seeing what is the longest common subsequence. What is common among P1, P3, and P5? First bit is common.
Second,
Yes.
yeah.
Second bit is common.
No.
No. So
Only fourth bit is common.
yeah. Third bit is common. No. This is yes.
Yeah.
Fourth bit is common.
Yeah. Yes.
Yes. And yes. And then fifth bit is common. No.
Is it different?
No. No. So when I say common, right, I think this is where the confusion is.
Okay.
So you cannot compare bit by bit in the sense.
Yeah.
Okay, now this is common. This is common. So it's not supposed to go that way. So
Okay.
when I say the fourth bit is common, if I say
Yeah.
this bit is common, every bit before it should also be common.
Yeah.
If I say this bit is common, every bit before this should also be common.
Yeah.
Got it?
Yes.
So from that point onwards, if you see, from that perspective, if you see, this is common, this is common.
Yes.
Correct?
P1
Is
and
that
P5. Yeah.
P1 and P5?
Yeah.
So that's why for the next two, I mean, for the next hop of two, we are able to merge this and this. I mean, we are just looking for opportunities where we can reduce the size of the table. And
Yeah.
how do we reduce the size of the table? We merge based on common sequence. If there was nothing common, then we just have to say we are not able to merge. That's
Yeah.
all. I mean, there's nothing that we can do about it. Okay. I mean, we can't do much about it. So similarly, I think Tirumala has asked, why are we taking 4 bits? I mean, this explanation would, I think, be sufficient for you. We're taking 4 bits because only 4 bits are common. If suppose, I'm giving you an example, imagine that this was 1. Okay. Imagine if this was 1. Let's change the question right now, Tirumala. Imagine if this bit was 1, then your answer would be 10011 star.
Yeah.
Got it?
Yeah.
So that's the difference. Just because the question has only 4 comments here, it's become that. But and then also it's P1 and P5. So 1 compression, 2 compression, 2 mergings, and then the P3 will remain alone.
Yeah.
Right? So does that answer your question, Tirumala? Or do you still have some questions? Yes, I think Haribabu's question is over, right? Uh, I mean, there's a question in the chat, so that's why. Are you able to get it?
Yes, sir.
Okay. Right. Okay, fine. Again, simple rules here. Always go left to right. Common sequence, it has to include the previous bits also. It's as simple as that. You can close your eyes and you can answer these questions. And again, for the previous questions also, the moment they ask what is the height,
Yeah.
okay, these are all just shortcuts I'm telling you. So if they ask what is the height of the trie for 1-bit binary trie, you don't even have to construct anything. You just have to add 1 to the longest prefix that you see. That's all. That'll be 8. Only for path compressed trie, you have to compress. You'll have to construct it to make sure that you get the answers. These are some shortcuts to answer these questions. But yeah. Okay. Now there's again one more question on. Okay. Just a moment. Okay. There's enough space now. Okay. So consider the prefix database shown below. What is the root lookup sequence to reach the destination address 101000000 in 1-bit binary trie? Right. It's all the same question asked in. Oh, okay. Can you please minimize views of other students and maximize your screen? Okay, Raghu, I think I think you have to do that. I think you have options on your screen window where if you look at, oh, got it. Fine, good. Okay, so let's consider. Okay, while I'm like, I think at this point you should be able to construct a 1-bit binary trie. I'm going to construct it here also, but I'll give you a head start. Construct a binary trie in your notebooks if you have it in front of you. I'll start in 2 minutes. Okay, I'll also construct it right now. First, we are putting P1. I mean, the first one is always going to be like this, if nowhere, and then P2. So it's a 0. So we go left. Put a 0, and then we say P2, right? And then P3 is 1 1 star, right? So this is 1 empty node, 1, and then P3 comes. And then P4 is 1 0 0 star. So it's 1 and then 0 and then 0, and this becomes P4. P4 is done. Now P5 is 1 0, so 1 0 1, and then once again a 0. This is P5. So this is the completely constructed trie. I hope you got it. If you did not get it, then unmute and let me know you didn't get it, and we'll analyze where you made a mistake. This is, I think, should be simple enough. But even if it's not the case, it's completely fine. That's what we're here to discuss and clear out. Okay. So we can proceed from this point. So again, what is the question here? The question here is, okay, I'll give you like 1 minute to figure out if it's the same. I think it should be, everybody should be able to. It is like, if it's 0, you go left. If it's 1, you go right. Anyway. So now this is the lookup table that we have in our hands. Agree? And internally, the router is going to have this representation. This is how it's there inside the router's memory right now. Now the question is, what is the root lookup sequence? So what is this root lookup sequence? So when you look up something, in the sense, you are getting a packet inside this again, if you have any questions, I think you can ask me. So I think Rashmi was typing something. So if you have it, you can always unmute and speak also. It's going to be fine. So if this is the input packet, right? So the input packet has what is the sequence? The IP address sequence 11000000. This is the input sequence. So what happens when such a packet comes? So what happens is, it takes the first bit and then it sees, and then it compares. Right? It compares as to where it has to go. And then it takes the second bit and then it compares the third bit and then the fourth bit and then the fifth bit. Likewise. Right? So can you uh, figure out what is the right sequence here? Okay. Okay. Answer is C. Perfect. Rashmi and Tirumala, right. Three. C is perfect. It's right, left, right, left. Why is it right, left, right, left? It is right, left because first I'm taking one. So for one, I am moving right. One right, and then I'm taking zero. And then I'm moving left. Yeah, correct. You're also right, Haribabu. And then once again I'm seeing a one, so I'm moving right. Then once again I'm seeing a zero, and then I'm moving left. So right, left, right, left. That's it. It's as simple as that. Okay, okay. Number. I think I lost some questions here, but it's okay. We can complete it. Okay, so this question is directly from the videos. So we have mostly looked at path compressed trie, right? So there is also something called multi-bit trie and level compression trie. This session is too short for us to look deeply into level compression and multi-bit trie, right? So which of the following statements is slash or correct? Right, so for this, a path compressed trie is an efficient way to compress a trie when nodes are sparsely populated. This one is true. So A is there. So a level compression trie is an efficient way to compress a trie when nodes are densely populated. So um, when the nodes are densely populated, right? So you can club them into triangles like what was shown in the video. This is also true. I mean, it's directly from the video. If you see the video again, you'll be able to answer this question. And then path compressed trie is an efficient way to compress a trie when the nodes are densely populated. No, it's wrong. This is the converse of A. Correct? Either this is true or this is true. This is false. And multiple trie can improve route lookup performance. Yes, this is also true. Right. So this is just a theory question. It's directly from the video. So now, next question is. This is an interesting one. So given a destination address of this particular sequence in a binary trie, what is the first step during the IP lookup? What is the first step during the IP lookup? Right? Is it traverse to the left, traverse to the right, randomly choose to move left or right, alternate between left and right traversal? What is the answer here? You should be able to answer this question at least at this point, probably. Sorry, yeah. Why right? Why? Okay, yeah, good. Why is it right? Why is the answer B? Your answer is perfectly right, but why?
The first bit is right, sir. 1.
Exactly. That's all. Simple. You don't even have to exactly perfect. Good, good, nice. So you don't even have to the moment you see okay in a binary trie. The moment you see this, you should not like just mechanically go ahead and draw the trie and then answer the question. See if you can answer the question before you can even draw it, because there is one you're matching right. This is directly following from this particular question, right? So like right, left. The same uh, strategy goes here as well. Okay, now this is, I think, an interesting question. Consider the prefix database table shown below. How many fewer nodes will be needed to represent a path compressed trie compared to a 1-bit binary trie? So because they're asking comparison between path compressed trie and 1-bit binary trie, you don't have a choice. You basically have to draw and then compare and then see. So the question is, how many nodes are lesser is what they're asking. The number of nodes that are less. So let's give it a shot. So now first I'm drawing the 1-bit binary trie. So this 1-bit binary trie and binary trie, they're all the same. They might sometimes they might say 1-bit, and sometimes they might just say binary trie. You should treat it as the same, right? First, let's draw the 1-bit trie. This is P1, and then P2, and then 3, and then P4 is 1. You can also like try and answer this question if you can. So 1, 2 is P4, and then P5 is 1, 0, 1. This, right? 0, 1, 0, 1, 0. Right. Yeah. So this is the 1-bit binary trie. Okay, now where are all the places where you can possibly think of um, merging something? How many places can we think of merging something here? I can see two opportunities here. I mean, this is completely manual. So you can, okay. So you can merge this part, and you can also merge this part. Agreed? So how will you match? How will you merge it? P1, P2 becomes 1. This becomes this, and then this becomes P4, and P3, and then 5. So the skip is equal to 2, and the segment, sorry, skip is equal to 1, and the segment is equal to 0, and the skip is equal to 1, and the segment is equal to 0. I think this should be clear. If not, you can ask me questions. Right, so now the question is, how many nodes have we reduced here? So there is 1 here, the nodes are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 nodes in this. Here, 1, 2, 3, 4, 5, 6. There are 6 nodes in this. So how many have we reduced? 8 minus 6 is equal to 2. So the answer is B2. That's it. It's as simple as that. So this is a very, I think this question seems to be highly repeated. So which among the following is true when the trie constructed with a set of prefixes resulted into a full binary tree? Sorry, trie, a full binary, oh, sorry, tree, right? So the answer again is both binary and path compressor have the same lookup and update complexity. The next is 4. Question number 4. Consider the prefix database table shown below. What is the height of the trie constructed using a 1-bit binary trie? Again, do we have to do this from scratch? Because what are they asking? What is the height of the trie constructed? Correct. So what is the height here? They're also saying the height of the root node is P1. If you apply the shortcut that was spoken about, you can always construct it also, but that will be a waste of your time. So look at the longest prefix here. So how many are there? There is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8. Add 1 because they are saying the height of the root node is 1 and then it becomes 9. So the answer is, oh good, Rashmi and Hello. The answer is D9. Simple. 4 and then it's 5. I think I kind of skipped some questions. Where is 5? Okay, maybe whatever I skipped, we can cover it next time. Okay, 6. Interesting. I don't see 5 here. All right. Given the prefix table provided below, identify which prefixes should be combined to minimize the size of the table for efficient storage in TCAMA. Wonderful. Okay. So I think this will probably challenge you a little bit more. Let's see, because most of you asked a lot of questions on this one. So let's solve this. So if you remember the rules that was told, right? Solve this question. I'll start solving in like 1 or 2 minutes. Okay. So what is step 1? Combine based on their next hops. So P1 and P5 are together here because the next hop is 4 and 4. And P2 and P3 are together here. The next hop is, this is step number 1. Now see if you're able to combine among the similarly colored ones. Right. You are right. Okay. So P1 and P5 and P2 and P3. But what will be the prefix there for P1 and P5? And for P2 and P3, what will be the prefix? P1 and P5, the prefix is going to be 100 0 star. What is it for P2 and P3? I want you to tell me. You answer perfectly right. I mean, this is enough, but what will be the prefix? The common prefix for P2 and P3. Oh, good. 110. Nice. So that's it. Six. Okay, so the storage complexity for binary trie, right? In terms of the number of prefixes and the maximum length of the prefix. So what are the number of prefixes? This is the number of prefixes. Here there are 5. So the number of prefixes are 5. Sorry. I think I should go to this one. So I'm just telling you, number of prefixes is 9 here, and the maximum length of the prefix is 8 here. Correct? That's what. So this is N, and this is W. N and then W. So what is the storage complexity? So as from the I mean, if you just watch the videos, you'll see that this has already been solved, and the answer is number of prefixes and the length of the prefix. So it's something like this. If you multiply 9 into 8, that will pretty much give you the whole storage space possible. So that's the worst case scenario. So we go of N into W. So the answer is N into W here. And so there is this algorithm called DIR 24/8 basic algorithm. So if you look at the video, so they basically have two levels of tables, right? So there is, so first they look up into one table, and then if you get a hit and corresponding to that, you get the next 8 bits. So it's explained in the video. So from that perspective, root prefixes that are longer than 24 bits are handled basically using a separate table, which is called TBL 24, the second table. This is directly from the video once again. There's nothing much here. Okay. Okay, so consider the prefix database table shown here. What is the skip value for the node P5 and the segment for node P9 and the trie constructed using path compress techniques. So they've even given you the answer. There's a skip in node P5 and P9. So let's quickly um, construct this. 2 0 1 0 1 0 P9. Okay. So basically this is the tree. I know it's not looking really good. So you must have gotten the same tree. So what are they asking? They're asking for P5 and P9. So where is P5 here? There is P5 is here. P9 is over here. So for P5, what can you compress? You can compress this two. And for P9, what can you compress? You can compress these three. There is a skip of 3 here. There is a skip of 2 here. What are you skipping? Which is a segment. The segment is 0 1 is what is being skipped here, and here is 0 1 0 skipping being skipped here. So what is the answer? The answer is D. Skip to segment is 0 1 0, because see they're asking the skip for P5, but the segment for P9, right? So segment here is 0 1 0, and the skip for P5 is 2. Is this clear? If it's not, you can always go back to the recording and then you can see and you can answer. Okay, so this question is about the TCAM. I told you TCAM is a parallel match, right? So imagine if an IP address inbound ingress IP address is this, and it yields matches at various locations: 4012, 2535, this one, this one. So let's say this is the TCAM table. Okay, and these are all the locations. Location 0, 1, 2, 3. As this goes, let's say 4012. Sorry. At 520, 536, and then it goes to 4012. Sorry, it goes to 1035, and then 2535, and then 4012. If it goes, keeps on going like this, okay. So this is basically the TCAM table. So this particular value 191.131.76.84 has matched with this, with this, with this, and with this. Again, you can have multiple memory locations. So what will you give priority to here? If there are multiple matches, which one will you choose? The answer is very simple. The very first match that you get is what you choose. So the answer is 536. That's it. Why do they do this? Because it follows from the same concept of LPMs. Let's say, see, you are matching here like this, and then the very first match that you get is what you choose, right? You might have more common subsequences below, but the very first match, if it says P6, you're going to P6. So similarly, it'll be ordered in such a way that the very first match you get is going to yield you the correct output. Let's say this might send it to hop of 0 or hop of 1 or hop of 2 or hop of 3. This will send it to the hop of 0. That's it. It's a very simple question. If you saw the videos, you would be able to understand this. Right. Okay. I think that concludes today's session. You can push off. Thanks. If you have any questions, you can ask. Or otherwise, we can conclude the meeting. Okay. Thank you, everyone. Much appreciated, Haribabu. Okay. See, I'll what I'll do is I'll probably I think I'll end the call for everybody. Okay. And the recordings will. You guys know where to find the recordings and the materials, right? I'll be putting it up on that particular sheet. If you don't know, then ask me. Then we can push off. Right. Okay. I'm ending the call for everybody. See you. Oh, I had to stop the recording.